All right, good morning, guys. We're here to finish our discussion of stoichiometry today and do lots of math problems together. So I want to start by kind of reviewing the tools that we have in our stoichiometry toolbox. Remember, we are counting amounts of reactants and products. We're looking at their masses and how masses of our reactants and products change as a chemical reaction happens. So our very first tool that we have is our molar mass. We learned how to find this from the periodic table, and we learned how to use it to convert from grams to moles or out of moles and into grams. We've also looked at, you can kind of see under my paper, that we have learned how to go from the number of moles to the number of particles. So that would be an atom, a molecule, or a formula unit, depending on what kind of compound you're working with, right? So we learned that we use Avogadro's number, or our number of items in a mole, which is 6.02 times 10 to the 23rd, really large number of items in one mole. We learned about why this number is so big. You've read a little bit about where that number comes from, but it's a tool in our toolbox. If we want to know how many items are in a set amount of moles. So if I had a beaker of 4 moles of water, I could do this math. I could do this unit conversion using Avogadro's number and figure out exactly how many water molecules I had in that beaker. Easy, right? And then today, our first one, we're going to add something to our toolbox, and we're going to look at this molar ratio. It is how we convert from moles of one thing into moles of another thing. So if you will, if you're a history buff, it's kind of like our Rosetta Stone that allows us to talk, to change from the language of one mole into the language of a different mole, or to go about talking about one chemical compound into a completely different chemical compound. So to illustrate this, I've got a balanced chemical equation for us. This is actually one that we worked with last week in lab. So we're gonna see this come to conclusion in lab on Thursday, but I wanted to introduce it to us so we can see. So I've balanced it for us. You see our coefficients there in red. What do those coefficients mean? Take a minute, think about it. Hopefully, you know that those coefficients tell us the amount of each type of atom we have every time this chemical reaction happens. So for this reaction to happen, we've got to have 2 atoms of aluminum, and that's got to combine with 3 units of copper chloride. I use the word unit there because copper chloride is ionic, it's not a molecule. Right? And then we produce, every time 2 aluminums and 3 copper chlorides react, we get out 1 aluminum chloride and 3 atoms of copper, right? So this is the micro scale. This is the actual atomic scale. So we could look at the masses of all these things off the periodic table, and that would be in atomic mass units, because we're looking at 2 atoms, 3 units, 1 unit, 3 atoms, right? Well, actually, we can look at this in the macro scale. So these numbers not only mean individual atoms and individual molecules and individual units, but they can also mean moles. So this tells us that 2 moles of aluminum react with 3 moles of copper chloride to make 1 mole of aluminum chloride and 3 moles of copper. Right. So since that is true, we can create ratios of these ingredients, if you will. So for example, we could relate each of these items, and we call those mole ratios because they're literally numbers of moles. So for this one, we could say every 2 moles of aluminum is equal to 3 moles of copper chloride. This is called a mole ratio. We are comparing moles required of one thing and moles required of another thing. Molar ratios are specific to the chemical equation that we are working with, right? This might not necessarily be true if we're reacting some other things, right? If we're doing some other chemical system. But for right now, in this system that we're working with, 2 moles of aluminum is the equivalent to 3 moles of copper chloride, because that's how they relate in our ratio, right? So we can create any number of molar ratios from this. We just have to compare and make a fraction, right? So, and if you need to see it, you can actually like write it out as an equivalent statement. So let's do one of those. So 2 moles of Al produces, you can think about it, 3 moles of copper in this system. So I can turn that into a molar ratio. 2 moles of aluminum is equivalent to 3 moles of copper. So when we look at these molar ratios, it's not like it don't feel like we're just pulling numbers out of the air. For our molar ratio, we want to find the number that matches the mole of the thing that we're looking. And we pull that from our balanced chemical equation, right? So don't feel like those numbers are being pulled out of the air. It's just like our molar mass. We're not pulling those numbers out of the air. We're pulling them from the periodic table. So for our molar mass tool, we are pulling those numbers from our balanced chemical equation or from our recipe. Right? Because we're going to be given a set amount of products and we're going to have to try to figure out how many times this recipe will happen. Let's say I had 10 moles of aluminum, right? I want to be able to figure out how many times this recipe can happen. If we got 10 and every time our reaction happens we use 2, we can pretty easily reason that this reaction will happen 5 times. If it happens 5 times, I'm going to make 5 times as much copper. I'm going to make 5 times as much aluminum chloride. Right? So we can see how our molar ratio here allows us to convert from moles of one thing to moles of another thing. Right? Another way to kind of think about and relate all of these pieces in our stoichiometry toolbox is this kind of mole island relationship. So let's pretend that we have a mole island. We've got moles of one thing in this village over here labeled A and moles of another thing in this village labeled B, right? We see this huge mountain range that connects them. If we want to travel from mole A to mole B, we have to go through this mountain range, and we're going to call this mole ratio mountain. We have to pass through or apply the mole ratio in order to go from moles of A to moles of B, right? Kind of think about it that way. Now, if we wanted to go to grams from mole A, you can kind of think about it like a little ferry boat out here, right? We're going to call it the gram tram. Let's say this is gram. We have to use our molar mass. If we wanted to travel to the particle party boat, I'm going to draw some music over here because they're having a good time, right? So this would be our particle party boat. We have got to apply and use, to get there, our Avogadro's number. Right? So this is just a visual representation of how we apply all of these different conversions, right? So if we want to go from mole A to mole B, we've got to pass through mole ratio mountain. We got to pull our mole ratio from our coefficients in our balanced chemical equation, right? Because it's going to link mole A to mole B. Maybe even mole C and D, right? If we want to go to grams of A, we've got to use our molar mass to get on the gram tram and go to grams of A. We could do the same thing for B over here. I could have another gram tram to get to grams of B. I've got to use my molar mass. And the same thing for my particle party boat, right? So Avogadro's number is what allows us to get there, right? So this is a visual representation of how we put all of these tools together. Okay, now let's apply this to some actual math problems. So here we go, or some actual good chemistry problems. So here's our first one. We want to know if we're told that 15 moles of copper chloride reacts completely with aluminum. It's the same chemical equation we just looked at, right? We balanced it. We talked about the mole ratios. We want to know if this 15 moles of copper chloride reacts completely. We want to know how many moles of copper will be produced. So if you are not good with word problems, here is a strategy that will allow you to kind of weed through all of the extra words. Because let's be honest, chemistry word problems can get just that, wordy, right? So there's a lot of extra words in there, a lot of clues. We want to be able to kind of hone in on what is important so that we can understand what our roadmap for this problem is going to be. So I know anytime I see a number in a unit that's going to be important. So we've got 15 moles and we got 15 moles of copper chloride. We're told that reacts completely with this aluminum. And we want to know how many moles of copper are going to be produced. So I've gone through and I've underlined the important stuff and I've boxed what I'm trying to find. I know at the end, I've got to get into moles of copper. At the beginning, you can kind of even write it right out of mole. I'm in moles of copper chloride, and I'm trying to convert that to moles of copper. Let's remind myself, we've already got our balanced chemical equation up here. We've got aluminum reacting with copper chloride to make aluminum chloride and solid copper. So I want to know here from moles of copper chloride to moles of copper. So looking at my toolkit, let me get my toolkit over here, my toolbox. My little design. Let's see. So I am right now going to convert from moles of one thing to moles of another. If I look up here, these are my toolkits. I've got my little drawing right here, right? Let's kind of orient ourselves to what kind of conversion we're doing, right? Do we know anything about grams in our problem? Does it ask us to convert to grams? Am I given grams? No, right? So I don't have to do that. I'm not asked anything about the number of copper atoms or the number of whatever that's reacting, so I'm not going to use this one. Let's look at this one. It connects moles to moles, and we're told we got to use our molar ratio, right? So my problem, I've got a mole, and I'm being converted into moles. Bingo, this is the one that we're going to use. So we've got to figure out how to use this molar ratio to convert from moles of copper chloride to moles of copper. So let's set it up. We always want to start with what we're given. So our problem down here, we're given 15 moles of copper chloride. So that's going to be my starting point. And I've got to figure out my molar ratio. It is my toolkit. It's my tool from my toolkit that allows me to go from moles of one thing to moles of another. If we're using our mole island kind of picture down here, I am right here in mole A. I've got copper chloride on this side, and I want to travel to the world of copper, right? I've got to go through the mountain range, and that's mole ratio mountain, so I've got to apply my molar ratio. So looking at the math, I want moles of copper chloride to cancel out. So where am I going to need to put a mole of copper chloride in my molar ratio? Does it need to go on the top, or does it need to go on the bottom? Hopefully you remember from our dimensional analysis that when we want something to cancel out, it's got to show up on the top and the bottom of our fraction. So if I want this to disappear and go poof and not be in my problem anymore, it has to have a counterpart on the bottom. What the unit I want to be in, which is my moles of copper, needs to go on the top. So I have to pull my molar ratio that connects copper chloride to copper. So let's go up to our balanced chemical equation and let's figure out what numbers we need. So I was trying to connect copper chloride to copper. So I see a 3 and a 3, right? So let's pull those numbers down and put them here. So for every 3 moles of copper chloride, I produce 3 moles of copper, right? So for this reaction, this is my molar ratio. Where did these numbers come from? Balanced chemical equation, right? So 3 and 3. And we see, some of you guys might be thinking, but wait, isn't 3 over 3 just 1? And the answer is yes. But it's good to get in the practice of doing it this way because our molar ratios right here won't always equal 1, right? Let's pretend we had done the same problem when we were converting from moles of aluminum to moles of copper chloride. That's a 2 over 3 molar ratio, right? So that won't, it's good for us to get in the practice of still multiplying it through. So to get this answer, right, our moles of copper chloride cancel because one's on the top and one's on the bottom. Now we just have to algebra the problem. So how do we correctly algebra this, right? We do whatever's on the top multiplied together, and we divide through by everything on the bottom. So we would do 15 times 3. We would divide that by 3, and we're going to end up with 15 moles of copper. right? So, not that hard. You just have to slow down and make sure you make your roadmap so that we know what we're converting to, what unit we're currently in, and what we're trying to convert to. And then we've just got to learn how we apply our tools to get us there. Okay, so let's take it to another level. So now, here's our problem. If 140 grams of copper is produced, how much aluminum was consumed in the reaction? So we're still using our same handy-dandy aluminum and copper chloride, right? So we want to know now, for doing our strategy, let's underline what's important, what we're given. So 140 grams of copper, and we're told that that's produced, right? We want to know how much aluminum was consumed in the reaction. We're going to say in moles. I forgot to include that, right? So moles. So how much aluminum in moles was consumed in the reaction? So let's write a roadmap. So I am given information in grams of copper, and I want to convert that initially, or right, at the end, sorry, not initially, into moles of aluminum. So let's kind of break this down. Do I have any tool in my toolkit that allows me to go directly from grams of one thing into moles of another thing? If I'm looking at my mole island here, I'm way over here in grams of one thing, and I'm trying to get to moles of another. So I don't have a toolkit or a tool that allows me to take a shortcut through the ocean over here around Mole Island to get to Mole B. I should see that I'm going to have to do multiple steps in this problem. I've got to convert first from grams of A into moles of A, and I've got to use my molar mass to allow me to go through the gram tram to get to that, right? So I'm looking at my toolbox up here. I'm going to go from grams to moles and get my molar mass, right? So that is going to be the first step of this problem. So I've got to go from grams of Cu into moles of Cu, and then I should be able to quite easily, since we just practiced it, go from moles of Cu into moles of aluminum. So this problem will actually be a two-step problem, right? So don't get confused. If you kind of make a roadmap out here, it should be quite easy for you to look at our toolbox and figure out what piece from my toolkit I've got to use to do each step of my problem. And this will take a little bit of practice until you get good and comfortable with it. But the neat thing about this is our problems, our stoichiometry problems from grams to moles and grams, we'll see eventually to grams, they work the same kind of roadmap every single time. So if you can get in the practice of dissecting your problem, making your roadmap, and then taking each tool to get each piece of your roadmap down here, you should start to feel more confident, more comfortable, and you should start to get these problems correct, okay? So let's do the math. So we're start out with 140 grams of copper. We've got our roadmap up here. So to go from grams to moles, and I'm going to need my molar mass of copper. And over here, to go from moles of this to moles of that, I'm going to need my mole ratio. So we're not scared. We're not just going to pull numbers out of anywhere, because we know that to get our molar mass of copper, all we have to do is pull out our periodic table. We know to get our mole ratio of moles of copper to moles of aluminum, all I have to do is look at my balanced chemical equation. So let's apply that now. So we start out with 140 grams of copper. My first step here is to go to moles of copper. So I've got to have the molar mass on the bottom, because the molar mass is in grams. So our molar mass of copper is 63.55 grams. And that weighs that is the weight of 1 mole of copper. So grams of copper cancel. Now I just have to algebra it. Now, if you like to do your problems step by step and get your answer and write it down, that's fine. I like to lump all my pieces together and do the math one time at the end. So that's the method that I'm going to use. But you could totally put this in your calculator and get your answer and then do this next step, right? So I'm ready to go. So if I look right here and I do my unit canceling out, the only unit I'm left with is moles of copper. So I'm right here in my problem. I've done my first step, and I'm ready to use my mole ratio to get moles of copper to cancel and be left with moles of aluminum. So to get moles of copper to cancel, if I'm building my molar ratio here, I'm going to need moles of copper to be on the bottom, so it will cancel. I want whatever I'm trying to convert into to be on the top, so that's moles of aluminum. So where do I get those numbers from? Right now, it's if I just did this, it would be 1 to 1, but that might not necessarily be true. So we've got to look up to our balanced chemical equation. So I'm showing that 2 moles of aluminum are required to produce 3 moles of copper. So if we look, 2 moles of aluminum, 3 moles of copper. Right? So these numbers come from the coefficients in our balanced chemical equation. So now let's algebra it. 140 times 1 times 2 makes 280. And then I'm going to divide through by my 63.55, and then I'm going to divide through again by my 3. You could also multiply these together and get one fraction at the end. It's just depending on how your mind works and how you would simplify this equation. So take a minute, grab out your calculators, and do that math. Okay, so I just did the math, and I got 1.47 moles of aluminum. If I look back to my problem, I want to know how much aluminum in moles was consumed. That's how much had to be consumed. So some of these problems will have more than 2 steps, right? But as long as we read our problem and we know what we started with and where we ended, we should be able to build us a roadmap to get there. We could add 10 or 20 different steps. But as long as we understand how to go from each piece of our problem, how to use our tools in our toolkit, we shouldn't have any problems. So let's do one more extension before we look at a whole stoichiometry problem. So let's say if I wanted to figure out how much this aluminum would weigh. I want to know how much I need, if I wanted to do this reaction in reverse and produce this much copper, how much aluminum am I going to need to weigh out on my scale? So I want to convert this from moles into grams. So if I'm building my roadmap, I'm in moles, and I want to go to grams, and I'm in moles of aluminum, and I want to go to grams of aluminum. So what toolkit up here allows me to go from grams to moles? You guessed right if you guessed molar mass. So I'm going to need my periodic table and apply my molar mass. So let's look at how we do this. We start out with 1.47 moles of aluminum, and I'm going to apply my molar mass. So what is going to go on the bottom this time? I've got moles of aluminum I'm trying to cancel out. So moles of aluminum has to go on the bottom, and my grams of aluminum has to go on the top. If I look at my periodic table, I see that the 1 mole of aluminum is reported to weigh 26.98 grams. Now all I have to do is algebra it. I thoroughly did my roadmap. I've gone from moles of aluminum to grams because moles of aluminum cancel out and I'm left with grams. So 1.47 times 26.98. So if I want to collect 1.47 moles of aluminum, I've got to weigh out, or I would weigh out 39.66 grams of aluminum. Sorry, this problem, we had consumed this much aluminum, so I would need to weigh out this much aluminum to start this process if I wanted to collect 140 grams of copper. Okay, cool. So hopefully that helped. Hopefully we're getting a little bit better at making our roadmap from our problem and seeing how we're going to apply our tools to get us there. All right, so let's look now at a full stoichiometry problem. So in this problem, we were going from grams to moles of another thing, grams of one thing to moles of another thing. We can actually go from grams of one thing to grams of another, and that would be considered a full stoichiometry problem. Right, so here is our last problem we're going to work together. If 12 grams of water decomposes, how much hydrogen gas will be collected in grams? So I've got 12 grams of water, and we want to know how much hydrogen gas in grams will be collected. So where do we even start for this problem? Because I know a lot of you guys are going to look at this and go, oh, I'm just going to give up. I don't even know what to do, right? So step by step, we need to understand and unpack what is going on here. We need to know what world or what island, if you will, we're working with. And we've got to have, we know to make this work, we've got to have a balanced chemical equation. So let's see if we can interpret our problem and come up with a chemical equation and see what's going on. How are our atoms and molecules and moles rearranging? So we know that we start out with water, and we see this word here, decomposes. So water is H2O. And when something decomposes, we have one thing that breaks apart into its pieces. So hydrogen and oxygen. So that would be H2, because we know hydrogen is a diatomic. And we also know that oxygen is a diatomic. So it's going to be H2 and O2. So this is not a completely accurate representation of this reaction because it's not balanced right now. So we need to go through and balance it. So I see that I am missing an oxygen off this side, so I've got to put a coefficient here. And then that changed my number of hydrogen. So my oxygen is now balanced, 2 on this side, 2 times 2 on this side. So I've got 4 hydrogens on this side and only 2. So now I can put a coefficient there. And this thing should be balanced. So this is our balanced chemical equation. And where are we going to go with this? So we know that we are going from grams of water to grams of hydrogen gas. So in my toolkit, I don't have a direct link between grams of this thing and, so let's see, let me complete my little thing over here. G of B, right? I don't have anything that follows me right here. I know I can use my molar mass. So I don't have a direct link between gram A and gram B, right? I've got to go through my mole island, and there are several steps. So if we look at our picture right here, we've got to use our molar mass to get to moles of A. I've got to go from moles of A over the mountains of mole ratio to moles of B, and then I've got to use my molar mass to get to grams of B. So if we're showing our roadmap for this, it's going to be multiple steps. So I've got to go from grams of water to moles of water, from moles of water to moles of H2, and then to grams of H2. This is my roadmap. Right, when we break it down into these individual pieces, it shouldn't be overwhelming for us because we know how to do each of these individual pieces. We can look at our toolbox or we can look at our map and we can see what we're gonna have to apply to take this trip, right? So let's get started. So to go from grams to moles, I have to have my molar mass. So let's start. So we know we start out with the number, the 12 grams of water, and I've got to convert that into moles of water. So my gram of water is going to go on the bottom, and my mole is going to go on the top. So 1 mole of water weighs how much? I can find that from the periodic table. I add up the weight of 2 hydrogens and the weight of 1 oxygen, and we should get approximately 18 grams. So this, once again, this piece is our molar mass. We aren't pulling these numbers from the air. We are calculating them using our periodic table, that tool that's in our tool belt that allows us to figure out how much 1 mole of something weighs. So if I were to follow my units, my grams of water cancel out, I'm left with moles of water. So looking at my roadmap up here, I've just done this part. Now, I need to do the next part. I need to go from moles of water to moles of H2. If I'm looking at my toolbox, or looking at my mole island picture, I've got to travel over the mole ratio mountain. Or if I look and I'm going from moles to moles, I've got to use my molar ratio. I get my molar ratio. I don't pull those numbers out of the air. I don't guess. I don't give up and throw my hands up and say this is too hard, because I know my balanced chemical equation gives me those numbers for my mole ratio. It's my recipe, right? Those numbers for my mole ratio come from my recipe. So what numbers do I use? If I look at my units, I want moles of water to cancel out. So right now it's on the top. It needs to be on the bottom. So mole of H2O. And I want to convert into moles of H2, so it's got to go on the top. It's what I want to be in. Now, I need to find these numbers. If I look up here, H2O has a 2 in front of it, so I need to put a 2 right there. H2 also has a 2 in front of it. This is another one where our molar ratio is actually just 1, but that's okay. So moles of H2O cancel. I'm left with moles of H2. So looking up here, where am I at on my roadmap? I've done this part. I've used my mole ratio to do this second step, and right now I am here in moles of H2, and I need to go to grams of H2. So how do I go from moles to grams? It's essentially the same thing I did the very first step, right? I have to use my molar mass. Now remember, I'm not just pulling numbers out of the air. I know that my molar mass comes from my periodic table. So look right here. I'm trying to cancel out moles of H2. So moles of H2 needs to go on the bottom. Since this is my molar mass, a gram of H2 goes on the top. And where do I get these numbers? I get them off the periodic table. Periodic table tells me that 1 mole of H2 is going to weigh twice the weight of 1 hydrogen, which is going to be 2.02 grams. So now we've got each of these steps out. Let's make sure that all of our units cancel. So we started out with grams of H2O, and we've canceled everything until we get to grams of H2. Is that what my problem asked? I started out with grams of water, ended up with grams of hydrogen gas. So yes, now all that's left is for me to algebra this. So however you like to condense your fractions, but if you have them strung together like this, everything on the top gets multiplied together and divided through by everything on the bottom. So I can do some canceling if I need to, or I could just do it all and throw it all in my calculator. So take a minute to do that. Okay, so I did my math, and I did it wrong the first time. So that's why it's important to do these calculations multiple times just to double check, because when you're dividing, sometimes it's easy to, mash an equal sign when you shouldn't, or whatever. Anyway, so I did this twice, and I got 1.35 grams of H2. Right. So a lot of these problems, you can ask yourself at the end, is my answer appropriate? Right? And a lot of times there's some overlap here. We could actually, without even doing another stoichiometry problem, predict the weight of our oxygen when this water is produced, because we know that mass is conserved. So at the end, the weight of each of my products is going to need to equal this 12 grams at the beginning, because that's how much I started with. Right? It's easy to see for this problem because we only had one source of mass at the beginning. It won't always be that clear for reactions that have lots of different pieces. But for this one, we can see that if our 12 grams, hydrogen is really small. The weight of it is really small compared to the weight of water. So we would expect our answer to be a lot smaller than 12. Right? Our oxygen is the heavier piece here, so we would expect our oxygen to have most of that weight at the end. So, okay. Hopefully this was a good kind of tutorial for you on how to do our full stoichiometry problems. Next, we're going to look at a situation where we have what's called a limiting reactant. So that's our last kind of topic in this chapter. And all that's left is for you just to get some more good practice doing this. So let's look at a scenario with a limiting reactant. All right, so sometimes when we mix amounts of reactants and products, most of the time actually, our reaction doesn't use up all of our ingredients. It's kind of like baking. Right? We only put a set amount of each ingredient to make our recipe. We don't want to have a lot of leftover, right, in there. If we put too much flour in and not enough of the other things, it's not going to taste right because there's going to be extra flour that doesn't react. Anyway, so chemical reactions are that same way. So let's say that we are doing a chemical reaction and this is our product, right? We can't change this chemical formula, right? So, if we're making this up, right, our chemical formula over here, we're going to say it's going to be yellow 1, red 2, right? And we've got our ingredients over here, so we're going to do yellow and red, just single by themselves. So they're going to combine to form this YR2 thing. So if this is what I start with, How many of these can I make? Right? So I'm told that 1 yellow combines with 2 red. Can I make another one? I can't, right? Why not? What is going to limit the number of things I can create here? I have extra yellow, but I don't have enough of the red. So for this one, the red is going to limit it. It's going to be the one that I use up first, or the one, according to my ratios, that I have the least amount at the beginning of. So let's kind of tie that into a chemical equation. So let's look back at our decomposition of water. So let's look at water. So we had H2O. Okay, so we're going to look this time at the synthesis of water. So this is the opposite of decomposition. I'm making just one thing. I'm making water. And I'm told that according to this balanced chemical equation, I have to have 2 moles of H2 and 1 mole of O2 to make 2 moles of water. So looking up here, which one, if I had equal amounts of hydrogen and oxygen gas, which one is gonna get used up first? Hopefully we're seeing that I require twice as much hydrogen as I do oxygen. If I have equal amounts of these things, let's say I had 10 moles of each and 10 moles of O2 to make this reaction happen, right? So the first time I do this reaction, right, I'm going to use up 2 and 1. So I'm going to be left with 8 and 9. The next time I do this reaction, I'm going to be left with 6 and 8. The next time I do it. So the number of moles of my hydrogen goes down by half each time because it takes 2, right? So there's an easy way to figure out, if you have equal amounts, how many times our reaction is going to go, and all you have to do is divide. So if I divide 10 moles by 2 moles, that tells me that this reaction with this amount of product can go 5 times. So I will create 5 times 2 moles of water. So if I use up all my hydrogen gas, I'm going to make 10 moles of water. If I use my oxygen, right, it's only got 1, so 10 divided by 1, this reaction can go 10 times. So I will make 10 times 2 of water, which would be 20 moles of water. This reaction won't really make 20 moles of water, right? Because I'm going to run out of hydrogen, right? So if we want to figure out which of these is our limiting reaction, if we have them in moles, we can figure out which of our reactants is going to get used up first. Which one is going to offer the least amount that our reaction, the least amount of times that our reaction can go, right? So that would, let's look at that practically in an actual problem like you would be faced in your Okay, so here is how our problems are going to work. These are arguably the most difficult in the chapter. So, if 15 grams of aluminum is reacted with 20 grams of copper chloride, how much copper will be produced? So, this problem, if we're using our strategy, let's look at the important things. 15 grams of aluminum, 20 grams of copper chloride, and I want to know how much copper will be produced. And we're going to say we want to know how many grams of copper that's going to be produced. So we've built a roadmap before with these problems. So what's different about this problem is, how do I know for my roadmap where I start? I'm given 2 amounts and asked to go to grams of copper, but I've got to figure out where I even start. Right? So obviously, both of these things are not going to get used up. One's going to get used up and limit the reaction, and one is going to be left over. So I've got to figure out first what my limiting reactant is going to be, because it is going to be my starting point. So for this problem, we should be able to build a roadmap once we know our starting point. So let's go through the process of figuring out which of these is our limiting reactant? So for limiting reactants, we've got to figure out how many moles of each one I'm starting with. So here's my balanced equation for this. So we are told that we have 15 grams of aluminum and 20 grams of copper chloride, CuCl2. So 15 grams of aluminum and 20 grams of copper chloride. We want to know, we got to convert these to moles. So how do we convert them into moles? We use our molar mass. So my molar masses come from my periodic table. So take a minute to convert both of these into moles. Pause the video if you need to, and actually work through that conversion. So we want to convert grams of aluminum into moles of aluminum and grams of copper chloride into moles. So hopefully you've had time to do that math, and we figure out that if we start out with this amount of reactants, 15 grams of aluminum and 20 grams of copper chloride, that means that we have 0.55 moles of aluminum and 0.15 moles of copper chloride. So now we want to look at our recipe for this reaction. We're told that 2 moles of aluminum react with 3 moles of copper chloride, right? So we have to figure out what portion of these moles is going to get used up first, or which one is going to get used up first. So we want to figure out, and this one is interesting because it's going to be a fraction, right? And that's okay, because really these are millions and billions of particles, right? So sometimes only half a mole reacts, and that's okay, right? Because that's all that we have. We're just shown that these ratios, it takes 2 of this for every 3 of that react. So we can divide our number of moles by its stoichiometric coefficient, or this coefficient here, so 2. So if we do that, we're told that this reaction can happen if I use up all of my aluminum, my half a mole, right? That this reaction will only happen 0.275 times. Now I do the same thing, 15 moles, but I divide by 3 because that's my coefficient, right? So this number, if this one gets all used up, 0.05 times. So which of these is going to limit how many times our reaction can go? Which one is going to get used up the fastest? Can you tell? Can our reaction really go this much? No, I don't have enough of this one. So whichever one gives us that smallest number there is that smallest number of times our reaction can progress, is going to be our limiting one. So for this scenario, our 20 grams of aluminum, even though it's more, it weighs more, is really going to limit our reaction. So it is going to be our limiting reactant, this 20 grams of copper chloride. All right, so we're going to use it if we're looking back at our starting point. Since we figured out that it was our limiting, it is going to be our starting point. So we don't even need to know this, so we're going to be able to figure out how much we have left over of it at the end. So we are going to start with our limiting reagent and the amount, because it's going to be the one that gets completely used up. So if we're building our roadmap, we're going to go with grams of CuCl2, and we're trying to convert that to grams of copper. And we know, looking at our toolbox, let me find it. We know, looking at our toolbox over here, that we don't have a link from grams of one thing all the way to grams of another thing. We've got to go through Mole Island and do our full stoichiometry. So if we're building our roadmap, if we're looking here, we've got to go from grams of our first thing to moles of our first thing. Then we've got to cross over mole ratio mountain to get to moles of our second thing. Then we've got to use our molar mass to go on the gram tram to grams of that second thing. So we've got a gram of copper chloride that I'm going to have to convert to moles of copper chloride. Then I'm going to have to convert to moles of copper, and then I've got to go to grams of copper, right? We should start to see that there is a pattern here. We go from grams to moles, moles to moles, moles to grams for a full stoichiometry problem, right? That same way, that same pattern every single time, right? So let's do it. So we start out with 20 grams of copper chloride. And I'm going to convert that into moles of copper chloride using my molar mass, which I just found was, if I'm looking up here at my thing, this was our copper chloride, so its molar mass is 134.44. I'm not pulling that number out of the air. We calculated that number from the periodic table. Grams cancel. I'm left with moles of copper chloride. So now, my next step is to go from moles of copper chloride to moles of copper. And I use, if I'm looking at my picture, I've got a crossover mole ratio mountain. Mole to mole is my mole ratio. I get that from my balanced chemical equation. My moles of copper chloride is what I'm in now. It's what I want to cancel. So it has to show up on the bottom. And my moles of copper is what wants to go on the top. So now we've got to find our coefficients here. So if I'm looking at my recipe, I see a 3 in front of the copper chloride and a 3 in front of the copper. So now my moles of copper chloride cancel. I'm left with moles of copper. I'm here at my roadmap, moles of copper into grams of copper chloride. So I need to go from 1 mole of copper, or sorry, grams of copper. I think I said copper chloride. Anyway, so now I've got to find my molar mass of copper. So the molar mass of copper is 63.55. I find that from my periodic table. And there we go. So now all I have to do is algebra it, and I will figure out if I have this much at the beginning, how much copper is going to pop out. We've already figured out we can kind of ignore this because it is our excess reagent. We're going to have some extra. This is what is going to determine or limit how much my reaction can progress. So it is going to directly determine how much copper is made. So all I have to now do is algebra this, right? So take a minute to do that and we'll return and see if you got it right. So if you do that algebra, you should get 9.45 grams of copper. So a lot of times these problems will ask you how much extra of our excess reagent will be left over in that pot. And that is not necessarily a hard question to answer. So you, since all of these things are related, we could pick this 9.45 grams of copper and convert that into grams of aluminum. And that's going to tell us how much aluminum we actually used up to get this 9.45 grams of copper. Then we just have to subtract to figure out how much is extra. Since you already converted some things to moles when we found what our limiting reactant was, you could just easily do a moles to moles calculation and then figure out the extra moles of aluminum that you have and how much they weigh. So there are multiple ways to kind of figure out those kinds of questions, and I will let you guys read in the textbook and figure out how best you reason through to be able to answer that question. But anyways, I hope this helped you work full stoichiometry problems and figure out how to find what is going to limit how much a reaction happens.